So are we okay with 1 and 2? Yeah? Okay, here's my 3. How are we doing out there? You have a question on 3? Okay, can I get y'all to calm down just a little bit? Is everything okay out there? Y'all are exciting. Y'all have fun.
So that one, when you do 3 times 0, does that cancel that x? So
It'll take that out
so
with
it's
it.
going to be 3x squared. So
Um, yes, that is correct answer. All right. So number 4. Let's see if I can do this correctly. 64 plus 4 squared times 3 is 40. 8h plus 12. Yes, ma'am. I did. I did very briefly up here where I foiled the 1 plus h to get 1 plus 2h plus h squared. See right there at the top. Then I distributed the 3 through that. Good. All right. Okay, real quick, I'm going to talk through number 4. I've already done the expansion. You should know how to expand that. Now, if you can do that without making a mistake is a completely different story. But expanding that, just remember that when you expand, you do need to think of it as 4 plus h, 4 plus h, 4 plus h. Please do not distribute an exponent. That's against the laws of math. And I did that. I used kind of a little cheap shortcut to jump straight to the expansion. You should have had that when you expanded it. And in these problems, we've done these before, but I'm going to reiterate this. After you expand everything, everything without an h should subtract away. If it doesn't, that's an indicator that you've messed up. Out of the remaining things, you can factor an h. So if I take an h out of everything left, I've got 48 plus 12h plus h squared. And then that h that you factored out will cancel with the h in the denominator. And then we can apply the limit as h goes to 0, replace all of the remaining h's with zeros, and those will go away, and leaving you with a 48. Are we good? The solving process of these is very repetitive. Very repetitive. The only time it wouldn't be is if there's like a square root or a stupid fraction or something like that. But these are all polynomials where the expanding is not, shouldn't be terrible. Are we good out there? You're out there? How's 5 and 6 coming? I honestly think 5 and 6 are a little bit easier because you don't have to worry about things like what is 4 cubed. Right? It's just x's and h's. All right, here comes my 5. Here's my 5. I tried to color code the things that canceled. You should get 2x minus 3. We okay? If you miss this, it's almost always because of some algebra mistake. You messed up parentheses, you distributed wrong. Are we good? You want to see 6? Everybody else? I heard a lot of yeses. Okay, number 6. Where'd it go? Oh, whoops. There we go. All right. So before we talk about 6, a trick that you can use for expanding, because anything cubed and higher does tend to be a little bit difficult. The coefficients of any binomial expansion, a plus b to any exponent, the coefficients follow Pascal's triangle. And so if you want to know what a plus b to the 0 is, that's the top row. A plus b to the first would have coefficients of 1a and 1b. A plus b squared is 1a squared, 2ab, 1b squared. So I can do Pascal's triangle and I can see the coefficients of my cube. It's 1, 3, 3, 1. And then the exponents, it starts with a cubed and the a's go down by 1. And it should finish with b cubed. going down by 1 from the right. And so when I expanded it, I didn't write it out and do it in great detail. I just did that. I knew the coefficients were 1, 3, 3, 1. And then I knew what pattern the exponents needed to go for the variables. It's a little bit quicker. And that's actually what I was doing when I expanded 4 plus h cubed on the other one. It's just a little bit more difficult when you have a number versus when it's just x and h. But you should have ended up with 3x squared minus 2 on this one. But again, it's the same process. You expand, everything without an h goes away. You factor an h out of what's left. You cancel that h with the h on bottom, and you plug in 0 for the remaining h's every time. Yeah. I say every time, unless there's something like a square root and you have to end up using conjugates or something like that. I guess that's up to you. Any questions there? Comments, concerns? Yep. Don't worry about the other side yet. We're not. That'll probably be something we do next week. Yeah, please do not attempt the back. Please do not attempt the other side because that's for the future. That's coming down the road. So, where we are going to be using stuff like this is when we are finding the slope of tangent lines, which is one of the main things we'll do in calculus. So we're going to bridge into taking some notes here. And we're going to find the slope of tangents with limits. There's a way to do it without limits as well, and if you happen to know that way, you can use that method to check your answer, but for now, I want you to actually use limits to get the answer. I may even show you the other method Tuesday or Wednesday. Did I see on Wednesday? Yeah, Tuesday or Wednesday next week. But the slope of tangents with limits. First, I guess we need to know what a tangent is. A tangent is a line that, and this is a Carboni definition. A mathematician would look at this and probably cringe or squinch his face up really funny. But I'm going to say it's a line that just balances on a curve. Okay, so graphically, if I have a curve of f of x that does this, the tangent would be a line that just kind of sits and rests on the curve. It could be underneath, it could be a line down here, but it just kind of balances on the curve at one particular point. If you remember back in geometry, a tangent to a circle was a line that just balanced on the outside of a circle, kind of the same thing. All right, so that is the tangent. The point where the tangent is hitting the curve, this point right here, this point right here, that is called the point of tangency. Point of tangency. And the idea behind the tangent is, we're not going to worry about that. So that's a tangent. Are we good there? There's also something called a secant. Do you remember what a secant was in geometry? A secant in geometry, don't write this down, was a circle with a line that intersected it twice. That was a secant. So similarly, in calculus, the secant that I'm going to reference is a line that intersects a curve twice. So if I have a curve, well, I'll just draw this one up there. So something that looks kind of like that again. A secant would go through the graph twice. That's a secant. Are we good? We're good. Now, you may be looking at one of these tangents up here, and you might be thinking, hey, this tangent right here, it does balance right there, but does it not, if I continue drawing it, does it not cross and touch the curve a second time? And it does. So technically, that is also considered a secant. However, when we call something a tangent, we really only mean in a very small window. It's a tangent right there. And what happens far away from that point is irrelevant. It's still a tangent. Good, bad, ugly? Okay, So our goal, our objective this year, no, well, for the next week or so, our objective is going to be to find the slope of that tangent. So our goal is to find the slope of the tangent. And the slope of the tangent has a lot of real world applications. If you have a graph or something that represents position, the tangent slope would represent velocity. If you have a graph that represents profit or something like that, if you're in economics, marginal revenue would be found by tangents, would be found by with calculus. So there's a lot of applications to tangents. And so to find the slope of the tangent, we're actually going to start with the secant. And the best way I'm going to freeze that for a second, to do this would be to do a real example rather than weird math definitions. So I'm going to look and make sure I have the right equation. What was the equation I wanted to do? X squared minus 3 at the point 2, 1. Okay, so we're going to find the slope of the tangent. Find the tangent slope. I'll say slope of the tangent. I'll go that way. Slope of the tangent. What did I just say? To y equal, I'm going to call that f of x. F of x equals x squared minus 3 at the point 2, 1. The slope of the tangent of that curve at the point 2, 1. All right, so here's what it looks like. Unfreeze, unfreeze, unfreeze. There we go. So here is x squared minus 3. You should know that's a parabola that opens up, and you can see the green tangent line right there. And if you know what the graph looks like, and you know where the point 2, 1 is on the curve, you could look at that and you know that we're going to get a very steep slope. I'm expecting an answer of 3, 4, 5, somewhere around in there. That's a pretty steep positive slope. But we want to find out exactly what that slope is. And the way we do that, our mechanism for finding that tangent slope, is we're actually going to start with a secant slope. We're actually going to start with the secant slope. And to do that, what I'll do is I'm just going to pick some random x coordinate, some random point somewhere else on the curve. And I have a little x right there. I'm going to pick this point right here. And I always want to include the point of tangency. I'm always going to include that point 2, 1. And so if that's my secant, looks something like this right now, I want to find the slope of that secant, and we're going to do the slope with algebra right now. So this is going back to that rate of change thing that was in the video. We're just going to do f of x minus f of a over x minus a. I already have this point 2, 1, right? To find the slope of this red line, I need these coordinates right here, okay? I don't know what those coordinates are. So what I'm going to do, I'm just going to call that x. And if my x coordinate is x, what do you think my y coordinate would be? Okay, y is not wrong, but I like to use as few variables as possible. And my y coordinate is found by doing x squared minus 3. So I'm going to say x squared minus 3. And I'm going to find the slope of that secant, which will be change in y, x squared minus 3, minus the other y coordinate, which is 1, over x minus the x, which will be x minus 2. And then I'll clean that up, and my slope right now is x squared minus 4 over x minus 2. And that is the slope of the secant line for any point on x. If I put x here, I can just replace the x with whatever that x coordinate is. Right? So I have some expression that represents the secant slope. Yeah? But then what I want to do is take that secant and I want to turn it into the tangent. Right now that secant is nowhere close to being the tangent. My tangent's going up, my secant's going down. They're not even close to the same. So what I'm going to do, I'm going to turn the secant into the tangent by, and here's the graph of it right here. I'm going to take this second point right here that I just randomly chose way the heck up there. I'm going to take that point, and I'm going to drag that point further down the curve, and I have an x on the x-axis down there. I'm really taking that x that I chose, and I'm moving it to the right. And as I move that x to the right, look at my secant slope and how it changes. Right now, my secant slope is negative. If I keep moving this point to the right, if I keep taking this second x point and I move it to the right, now look at my secant. The further I move my x to the right, my secant slowly starts to kind of become the tangent. Are we seeing how it visually turns into the tangent? I keep moving my x a little bit closer to this x point here, to that x coordinate of 2. If that x gets closer to 2, look at that secant. As x approaches the 2, look at this. It's just getting there and it's closer. And look at the slope of the secant and how it compares to the slope of the tangent. The closer that x gets to 2, as that x approaches the 2, the secant will eventually, as x gets close to 2, it will eventually, pow! It became the tangent. Once that x approached the 2, once x got to 2, the secant became the tangent and their slopes were the same. We seeing that? I very carefully chose my words there. I kept saying x is approaching 2. So if I want to take this secant slope and I want to turn it into the tangent, I need the x, that second x point, to approach 2. What does that sound like? That sounds like a limit. So to get the tangent slope, we start by thinking about that secant slope. I take that secant slope and I'm going to analyze this secant slope, and I want to see what happens to that secant as that x gets ever so close to 2, and the answer to that limit will be the slope of the tangent. Yeah? So setting it up is the only new part. Once you get it set up, you then are solving limits. Can you solve that limit? Do I need to stop and let that marinate for a little bit? Yes, ma'am. That was my change in x. Remember when we do the slope formula, it's y minus y over x minus x. It's your old-fashioned Algebra 1 slope. Does that answer your question? Because that was not a, are you lying to me? But to find, we're finding the slope. Finding the slope between the points. We have one point that's really sexy, 2, 1, and the other point is a generic point like that. So it's we're subtracting y's and subtracting x's. I don't know. I kind of said the same thing over again. But has anybody solved this limit yet? What'd you get? That's what you should have gotten. X plus 2, x minus 2 is the numerator, x minus 2 on the denominator. By the way, if you set these these tangent limits up correctly, you will always get 0 over 0. If you don't, you messed up. And so that's something you could do after you have it set up. You may want to just try plugging in really quick just to make sure it's 0 over 0. If not, you need to fix something before you proceed. 2 plus 2 is 4, and that is in line with what I was expecting. I was expecting something a steep positive slope. Good, bad, ugly? Yeah? Yeah? Okay, that was a very specific example. I am now going to give you a very generic example, and this will end up giving you a formula that we can just kind of use to do this rather than having to think graphically and drawing all this stuff. So, so let's do a generic example. Find the slope of the line tangent to y equals f of x at x equals a. Okay, so very generic. We don't have an equation. We don't have a point of tangency. It's just very generic. And so I'm going to draw a generic f of x. So there's my f of x. I have a point x equals a. That is where I'm finding my tangent. So here's my tangent line. But to find the slope of that tangent, we started with a secant. So I'll just do this little secant here that also goes through the point A, but I will have a second point way over here that I'm just going to call an x coordinate of x. And if you know your x coordinate, You get the y coordinate by plugging x into the equation. So my points are a f of a, because this is a function y equals f of x. And the generic one over here is just going to be x f of x. And so my secant slope, the slope of that green line, is going to be change in y over change in x, right? And so I'll subtract my y's, which are f of x and f of a. So when I subtract those, my numerator is f of x minus f of a. My denominator, my change in x, I'll do x minus a. Where's my pen? There he is. There is my secant slope, and that is the rate of change that was in the video. I told you we were going to kind of bring it back to tangents, but it's just slope. That's old-fashioned Algebra 1 slope, the same one you've been doing for like 5 years. But then we apply calculus to that. We're going to turn that into the tangent by simply, I say simply, I don't know if anything we do here is simple, by analyzing that slope and see what happens as that second x coordinate moves closer and closer to that a value. And this is one of the two limit methods that will give you the slope of a tangent. That's one of the two. The other way is the one that uses h, which is what we were working on earlier today. So that's what the second way is going to be. We probably won't get to that today, but this is one of the ways. Yeah. So keep that in mind. Keep that formula in your mind. Have that memorized. We're going to do, how much time do we have? We have time to do like 8 examples, right? What? It's almost Friday. What are we on, like number 2 here? Find the slope of the tangent. And here's the beauty of these problems. I love these problems because I don't even have to think about how pretty the function is. I know these will always work out nicely if you set it up correctly. So I'm just going to make up a function. Find the slope of the tangent to f of x equals, let's make it fun. Let's do 3x squared minus 4x plus 1 at x equals, I want to make sure I don't do anything. Okay, let's do 2. What? Minus 5. Why? Okay. Is it? There were multiple people who felt that way. That's weird. Okay. All right. So when we set this up, until you have committed this to memory, until you have memorized this limit right here, I recommend that you always write it down in its basic form, f of x minus f of 2 over x minus 2. I recommend writing it like that every time until you have it memorized. Then, once you have it memorized and you feel comfortable with it, maybe then you could jump straight to actually substituting what f of x is. 3x squared minus 5x plus 1 minus, and what f of 2 is. So I've got to do that over here. 3 times 2 squared. Oh, crap. Who invented these numbers? Oh, is this really the is this the top one on the back of the is it the point x equals 2 also? Yeah. Wow. Okay, y'all suck. Okay, we'll do the first one then. So 12 minus 10 is 2, plus 1 is 3, so then we'll subtract 3. It is kind of weird that I so closely, almost randomly created the same problem on the back. Right? And now we have, this is the end of the new material. Once you have the limit set up, we are now channeling what we've been doing for what feels like 3 months. Right? 3x squared minus 5x. 1 minus 3 is negative 2 over x minus 2. And if you want to check to make sure that what you have is reasonable, plug in 2 to the top and bottom and see if you get 0 over 0. If you don't, you've messed up. You should always get 0 over 0. I'm going to trust my work. Can you factor this? You should be able to, because there's a huge hint in the denominator. Yeah, you know x minus 2 has to cancel. That's the beauty of factoring within a limit, is you have hints where you didn't have those in Algebra 2 and Pre-Calc, right? So if I know x minus 2 has to cancel, then I need a 3x squared. I think 3x times x will give me 3x squared. I need a negative 2, so I already have a negative 2 here. A positive 1 times a negative 2 would work. Expand. Or I'm going to double check to make sure we get a negative 5x. So 3x times negative 2, negative 6x, 1 times x. Okay, that works. I can cancel. Plug in 2 to what's left. 3 times 2 plus 1 is 7. And there is the slope of the tangent. Are we okay? Good? Good? All right. The video, hold on. You can put stuff up, but listen to me. The video, I want y'all to watch a video. It is originally like a 25-minute video. It's the longest one of the year. We probably just covered about 10 to 15 minutes of it. I want you to finish watching that. I'm going to link it, and I would like for you to watch it before you come to class Tuesday. So maybe during AO Monday, or Tuesday, I mean. I don't know. But I'll link it. You watch that, and that is it for the day.